Hi guys, welcome to Learn Electronics Repair. This is where I fix stuff and hopefully you learn how to do it, yeah? So I have here a powered mixer. I've had a few of these on the channel before. This one is a Samson TXM16 stereo powered mixer, 1000 watt. So we have quite a large stereo amplifier in the bottom of this and quite a large mixer panel. The problem with this one apparently is that the protect light comes on and stays on. So we have protect lights here, there's two of them. I don't know if it is on one channel or both, but I guess now is the time to find out. So I'll just get a power lead and let's see what happens. I have this ready to power up. I'm not going to put it on my light bulb current limiter because obviously the owner has already powered it up anyway, so it doesn't go bang. I've noticed that the amplifier mode here is set to bridge, so that might be something to do with why the protect light is coming on. Let's just switch it on and see what we get. Well, we don't seem to get anything. There's a switch on the back. Let me try again. Okay, so both protect lights are on. And do they stay on? Yes. Okay, let's just set it into main right, main left. So that's in stereo mode. Let's see if the protect lights come on now. Yes, and both of them are on, which suggests there's a problem with both amplifier channels. Okay, I've noticed this is bent, by the way. Can you see it? When I'm turning it round, you'll see. Maybe I'll just try and straighten that up. Okay, but I doubt that's anything to do with the problem. This channel is actually all turned down anyway. So I'll open it up, then I think I will disconnect the mixer from the amplifiers to see whether the problem is due to some voltage being sent in, a DC offset voltage from the mixer, because that would cause a protect fault, whether it's a problem with the amplifiers themselves, in as much as the output transistors or something has a problem, or whether the protect circuit just thinks there's a problem, like a phantom problem that there isn't actually there. The last time I had something like this, it was a broken track or burnt track hidden underneath a load of resistors at the back of the amplifier module. I don't quite recall if it was the same brand, but let's have a look. I've removed plenty of screws and I've now got the top off this, so let's have a look what we have. Okay, we can actually balance this back here. That's unusual. Normally the cables are not long enough, so that's actually rather handy. So we can see we have two cables coming down here from the mixer to the amplifier with quite a few connections on. And we have another one coming down here, which looks like it might go to a little voltage regulator. So that's what we have between the two units. So these will no doubt have some supply voltage rails on, and they will have the audio signals coming in from the mixer. So I think the first thing I'll do before anything else is just to power this up again and have a quick look at some voltages around it. I'll just try and find something to wedge behind this so it doesn't just hit my monitor behind it. Once I've measured some voltages, I'll probably end up just disconnecting this, so I've got just the amplifier unit if that's where the problem is, which it most likely is, and then we can work on this amplifier. I'm just having a quick look. There's a fuse here which is intact. There are two more fuses here which look like they are intact. There are two fuses this side. I'm not sure if they are intact or not. We can have a look. They might be blown actually. And that's all I can see in the way of fuses in it. Okay, I have it ready to go. let's take some voltage measurements. So the first thing we need to do is to find a 0 volts point. Yeah, the 0 volts. So looks like there's a ground pin down here in the middle. Let's just go on to resistance range. Is that connected to the chassis? Yeah, it is, because the chassis is probably... Oh, is it connected to the chassis? Let's get a good connection. Yeah, it is. The chassis is probably ground. There's a black wire here as well. Is that also connected to it? No, so we can't say that wire is actually ground. Let's go back onto the chassis again. How about this point? That's a 0 volts, so we can stick the probe in there, okay? It's a good place to leave that. Let's have a look then. So we have some fuses. I'll just check the fuses first. So there's a fuse here, which is good. Just tighten that up a little bit. 2 more fuses here. That's good. That's good. These are marked as 2 amp fuses. This is a 1 amp fuse. Okay. And then there are 2 6 amp fuses here. So these are probably powering the main amplifier because of the highest ampage fuse. That's okay. And that reads okay. So the fuses read okay. So the next thing then will be to measure some voltages. Just pop that into there. We definitely have a good ground. I'll measure the voltage on the fuses first. So normally the fuses will be connected from the AC of the transformer going into the bridge rectifiers. I can see the bridge rectifiers are actually under these 2 heat sinks. So I've put the meter onto AC volts. I'll just switch it on. Fans are running. I'll just check if it's still got the protect fault. Yeah, both protect lights are still on. So what have we got on these fuses? 88 volts. 88 volts. 11 volts. 18 volts. 18 volts, and this one. This has nothing on it, but this could be... Oh, let me just try again. This could be on the DC voltage rail. So let's just go to DC volts. See if we have anything on this one. Yes, 90 volts DC. Okay. I don't see another fuse, right. So we can say a few things already. The 2 fuses with the 88 volts AC, they'll be the power, as I said, to the main amplifier. Yeah, the 2 with about 18 volts on here, these will be generating a 15 volts supply, which will supply the mixer. That's normal. And it'll be plus and minus 16, and these will generate a plus and minus 88 or 90. Yeah. The one in the middle, which has the 12 volts on, roughly will be for a 9 volt or 12 volt supply. Could simply be for the fans. This looks like a little bridge rectifier in front of that fuse. That looks like another little bridge rectifier, possibly. Oh, yeah, it says D byte for diode, so probably R. These are the large bridge rectifiers. There's 2 of them. It's possible that they're both actually on the 90 volt rails, maybe, or it may just be that one is on the 15 and one's on the 90, but I don't think so, because there's one here down by these fuses, so it might be that that's effectively on the positive and negative rails. Just seeing if these heat sinks are touching each other. They don't look like they are quite. I'm not sure they should be. Well, there's no connection between them anyway. I'm sure we haven't got any short circuits because no fuses have blown, otherwise you'd expect a fuse to blow. So the next thing to be will be to find the DC voltages, the plus and minus 15, the 12 volts, I guess. Okay, so probably if there's going to be a plus and minus 15, it will show up on the cables going to the mixer section. Yeah, somewhere in there I'd expect to find a plus and minus 15, plus and minus 12, maybe something like that. The plus and minus 90 will appear on the main output transistors. So let's have a look to see if we can find the voltage rails. They're not marked on here. Okay, are they marked on here? No, not marked on here either. But this looks like it's probably supplying voltage rails up into here, and then from here into here to the mixer. So I'm guessing we could look on the power supply here, we could look here, we could look here, whichever's easiest to get to. Let's try it. Can we get? Yeah, I can get to this one easily enough. Okay, let's look for the voltage rails. So leave the black lead in the ground. We're on again. What have we got? Well, we need to go to volts range. Okay. We've got looking for plus or minus 15 or thereabouts. Nothing on that one. Nothing on that one. Nothing. Nothing. And make sure I have a connection on the ground. Oh yeah, I had a bad connection on ground. Okay, minus 14 there. I think we can use the metal chassis as ground actually. Let's get a connection onto it. Yeah, we can. Right, let's have a look again. Start from this end. Nothing. 5 volts. So there's a 5 volt supply. That sounds fine for logic circuitry. I think there's a digital section of this mixer. Nothing. Minus almost nothing. Get back, actually get at it. That's the minus almost nothing. Plus 24. Minus 14.6. Nothing. Plus 14.95. That's the plus and minus 15s. Nothing. So we've got plus and minus 15. We've got a 24 volt. We've got a 5 volt. So they all sound reasonable. Now let's have a look on these transistors in the middle pin. So these should be the collector. And either one side's going to be the positive half and one the negative half, or the front part the positive and the back half the negative. Let's have a look. 45. So this is plus 45. This one. There's difference, plus 45. What's on the one towards the back? So this half looks like it's a positive supply. It has a 45 volt supply. So you'd expect this side to all be the negative. Minus 90. Well, this tells us straight away there's something wrong. Yeah. So on this side, the main supply is 90 volts. But on this side, it's 45 volts. Okay, let's switch it off and let's think about that for a little bit. It's likely, and this probably explains why there's 2 bridge rectifiers down here now. This is probably a class G or a class H amplifier. And I'll explain to you what that is. That also sort of explains why we have these big transistors, which are different from the others. You see that one and this one, and then these 3 are different. Yeah. And then we have that one and this one, and those sets of 3 are different. Yeah. And then we have some sort of driver devices. Okay, let me just explain to you what I think we have here, and then we can check some more. Let me explain how we can have a minus 90 volt and plus 45 volt supply on our amplifier. Because I think you'll agree that means something is wrong. But let me explain to you quickly how these amplifiers work, and then I'm sure it'll be a lot clearer. I did a whole video, by the way, all you need to know about amplifiers to fix stuff, and I've explained this in detail. So I will link that video here, and then if you want to know more, you can watch it. But basically, most amplifiers are Class B or Class AB amplifiers. Class B doesn't mean they're not as good as Class A, by the way. These Class A and Class B and so on, CD and more, are different types of amplifier, or if you like, the principle, the topology, the layout of the amplifier. So many amplifiers are Class B. And the way this works, you have an NPN transistor connected to a positive voltage supply. The base is being driven by the audio waveform, and on the emitter we have a low value resistor. These are power resistors, several watts, 5 watts, 10 watts, more depending on the circuit, and they're typically about 0.22 ohms. I'll use R for ohms, that's common, so that's just so that you'll see it, but we could put ohms. And then we have from here another resistor going to a PNP transistor, and this is connected to a negative power rail, positive, negative. Okay, the speaker connects to the junction of these two resistors, and this connects to ground. So that is a typical amplifier circuit. There will be some more resistors in here to set the bias of the transistors, and I'll just draw them and explain basically what they do. So we have resistors like this, and then we can have some capacitors here, and then this point is where you send the signal into the amplifier. This is in. Comes from a pre-driver stage. If this is the output stage, you'll have several stages in front of it to gradually increase the amplitude of the signal and the power, but that's where it comes, and the input signal is other side is connected to ground. The reason for these capacitors is to not affect the DC voltage on the transistor bases. Okay, now for an NPN transistor to switch on, you need to put voltage on the base, but transistors being transistors, these are bipolar transistors, you have to put about 0.6 volts on the base before it will switch on, and this is positive, yeah, with respect to the emitter. So if you were to measure from the emitter to the base, these resistors are chosen so that you get 0.6 volts. Okay, didn't leave much space, did I? For a PNP transistor to switch on, it's the opposite. The base needs to be negative with respect to the emitter. So if you were to measure from the emitter to the base on this side, you will find 0.6 volts negative. And those voltages are created by the ratio of these resistors. Let's put some voltage supplies on here as well. So let's say we've got a minus 45 volts, and we've got a plus 45 volts. Okay. Now, the way the amplifier works is, at the input you have an AC waveform. This is your music. Okay. This is the center point. This is 0 volts. So the waveform is going positive and negative with respect to 0. And this capacitor will, and this one for that matter, will add the waveform voltage to the bias voltage. This 0.6 volts is called the bias voltage. Okay. So on the positive half cycle of the waveform, the voltage on both bases will increase. They'll both go up, and the amount they go up will depend on the amplitude of the waveform. On your NPN transistor, as I said, you need to have more than 0.6 volt positive on the base compared to the emitter to make it conduct. So as this waveform starts to increase, the voltage here starts to go up, and that turns the transistor on. The transistor starts to conduct, and the current flows into the speaker and down to ground. So the speaker cone moves in one direction. Let's say it goes outwards. Okay. The reason the current goes through the speaker into ground and not down through this transistor is because when the voltage on the base here increases, this switches on, but the voltage here also increases by the same amount, so it becomes less than minus 0.6. Yeah. If you think about it, adding any positive voltage to a minus will make it less minus. Yeah, until it crosses 0, then it also becomes positive. So this transistor, which was almost switched on, switches off, and the higher the voltage goes, the more it switches off. At the same time, the more this switches on. So as it switches on more, we get more current through our speaker. My rubbish drawing. To ground, yeah. And that's why the current goes through the speaker. Gradually the waveform comes back down to 0, at which point this has just 6.6 of a volt on the base and it switches off. The waveform now goes negative. So on both bases, this one goes minus and this one goes minus to go more negative. So this one now switches more off. It's off anyway. It can't really switch more off, but it's certainly off. Yeah, it's more off if you like. This one starts to switch on. So what happens now, because this is a negative supply, the current flows through the ground, which is more positive than the supply, if you want to think about. It's flowing from positive down through this transistor to the negative voltage rail, and that pulls the speaker cone the other way. Okay, the more it switches on towards the peak of the waveform, the more current flows this way, down into your speaker, and the more the speaker moves this way, and then gradually the waveform comes back to 0 again, so the speaker cone comes back, and as it crosses 0, this transistor switches on, off. So your speaker cone continually moves like that. Okay, there's a couple of things you need to realise about this circuit. If the circuit is working properly, there's no faults in the circuit, and there's no input, so basically this is 0 volts, there's nothing coming in to switch either of the transistors on, the voltage here will be very close to 0 volts. Ideally it would be 0. It'll actually be extremely close to 0. Okay, because nothing's ever perfectly balanced. But for all intents and purposes, when there's no input voltage, there's no output voltage, the speaker cone is sitting in the middle position, and it's not being driven either way. There's no audio coming out. Okay. At this point, both transistors are switched off. So one important thing to realise with an amplifier output like this is if you've got no input, the output will be 0. There'll be 0 volts across your speaker, because this ground is also 0. Okay, so that's how it works. Now let's have a little think about a couple of issues with this. Not really issues, but let's just think about how it works a bit more. What's the maximum power we can get out of the amplifier? Well, the maximum power depends on the maximum current that will flow through the speaker, and your speaker has an impedance, let's say 8 ohms. Yeah, it's an 8 ohm speaker. Okay, so for a given voltage, and what's the maximum voltage that can ever appear on this end of the speaker? Well, it's either plus 45 if this transistor is fully on, or it's minus 45 when this transistor is fully on. So the highest voltage that can ever appear across our speaker is 45 volts at the peak. Yeah. In fact, because the waveform is continually moving, the average, or RMS, root mean square, we can consider it to be the average, is going to be less than that. Okay. But we can have a maximum of 45 volts across here, and the resistance of our speaker is 8 ohms. So how much current can flow in it? Well, we can use ohms law, it's quite easy. Yeah. V, put in the triangle, I, R. Yeah. Okay. we want to know the current. Current equals V over R. Cover it with your finger. I equals V over R. So the maximum current that can flow through our speaker is 45 divided by 8, which equals, quick calculator, 45 divided by 8, 5.625 amps. Yeah, that's the maximum current that can ever flow through our speaker. What's the wattage that we can get out of our speaker? Well, watts equals V times I. So 45 times the current, just clear that, 45 times 5.25, 236 watts. 236 watts. That is the maximum wattage we can get out of our speaker. What if we want more wattage out of the speaker? Well, there's two ways, and there's only two ways you can do that, really, with this circuit. One is to decrease the resistance of the speaker. So we can put a 4 ohm speaker, okay? This formula now is 45 over 4. Which, let's just call it 11, shall we? Rather than 11 point something, it's 11 amps. Yeah. And the wattage is 45 times 11, 495. I can do that one in my head. So by decreasing the resistance of the speaker, we can get more wattage out of it because we're getting more current through it. What if we want even more current? Well, we can't keep reducing this indefinitely. But what we can do is increase the voltage. So if we put more voltage in, then in this formula, V is more. So we get more wattage. In fact, in this formula, V is more. So we get more current. Yeah. Let's say we put 90 volts in. Plus and minus 90. We'll go back to this formula. We'll just use this one. Obviously, they both apply. Yeah. So now the current is 90 over 4. 90 divided by 4 is 22.5 amps. Yeah. So the current is 22.5. So the watts is 90 times 22.5. Shall we do it? 90 times 22.5. 2 kilowatts, yeah. That's a lot of watts, isn't it? But let's consider something else. Okay. These transistors. Do you think the transistor itself is dissipating the most power when it is not conducting? So effectively this end is 45 volts and this end is 0. Yeah, it's not conducting. Is it dissipating the most wattage then? Or is it dissipating the most wattage when it's fully turned on? So it's passing the maximum current of that example we used, 45 volts, yeah, of 11 amps. So is it dissipating the most wattage when it's passing no current, or 11 amps? Well, the answer is basically it's dissipating the same wattage at both points. And the reason is this. Watts, as we know, equals voltage times amps, yeah? When the transistor is off, we've got 45 volts on one end and 0 on the other. So the voltage across this transistor is 45. What's the current passing through it? 0, basically. There's nearest damn it. So what's the wattage? 45 times 0 equals 0 watts. There's no current flowing, there's no wattage. Yeah? What happens when it's switched fully on? Well, now the transistor is basically like a short circuit. Yeah? So the voltage across the transistor, as near as damn it, is 0. Yeah? And the current now flowing through our transistor is the 11 amps. Yeah? 0 times 11. What's that equal? Well, it still equals 0, yeah? So our transistor, when it's fully conducting or fully switched off, is not dissipating any power. But what happens when it's half on and half off? Yeah? So effectively, you've got 45 volts on this end. You've got about 22.5 volts on this end. Yeah? What happens now? Well, let's have a look at it. Well, the speaker now has 22.5 volts across it. Okay, so we need again to find out the current V over R. So we now have 22.5. Yeah? The resistance is still the same. 4 equals, well, it equals half of that. Yeah, which is about 5.5 amps. Yeah. What's the wattage now? Well, watts equals volts times current. We know there's 22.5 volts. We know the current is 5.5. So 22.5 times 5.5 is the answer. 22.5 times 5.5. The speaker now is dissipating 123 watts. Where's the rest of the wattage? Well, it's being dissipated by the transistor, because the transistor also has 22.5 volts across it. It's also passing 5.5 amps. It's the same current. So the transistor now is also dissipated 123 watts. So the transistor gets hot, and that's why this type of amplifier needs big heat sinks. Yeah. What happens now if we increase the voltage to 90 to get more power? Well, this suddenly becomes a lot more than it was. Yeah, it now becomes much more than it was, because we know the total current was about 2 kilowatts. This becomes about 1,000 watts. Yeah. So by increasing the voltage to get more power, we need to put massive heat sinks on the transistors. We need to put bigger transistors, yeah, if you like, or more of them. But we still need to get more wattage. So there's a way around this problem, and that's this. We can take here another transistor or a MOSFET. These could also be MOSFETs, yeah, very similar. And we connect it to a 90 volt supply plus. Yeah. And we do the same on the negative end. So here we take another transistor to a minus 90 volt supply. So we've now got the plus and minus 90. Yeah. These two transistors then, via some circuitry, they're controlled by the input signal, such that when the output waveform, let's just draw it, 0 volts, 45 volts, 90 volts, yeah, let's just draw it, okay, 45 volts, 90 volts. Okay. When the output waveform is going to go above 45, because we can detect that, we can detect it's almost at 45 and it's going to go up above that, we can turn this transistor on and increase the voltage to 90 so it can continue to go past. Yeah, and as it drops back down again below the 45, we can switch this back off and we can reduce the supply voltage. So the waveform comes down through here, and then again on the other side, once it goes above minus 45, we can switch the transistors on. In fact, we switch them on both together. You don't switch one and the other, you just switch them on. Yeah. So again, as it goes above that, this higher voltage is available. Yeah. Then we can switch it back off again. So that's what's happening with our amplifier. That's why our amplifier has both a 45 volt and a 90 volt plus and minus supply. So that is what is happening with our amplifier. Our amplifier is 500 watts per channel. We need more than the 236 watts with a plus and minus 45 volt supply. But instead of having a plus and minus 90 volt supply permanently, which generates a lot of heat, it uses a switching method. Okay, and this is called a Class G amplifier. Okay, and that's what we have, Class G amplifier. Now there's something wrong with ours. On the positive supply we have 45 volts, but on the negative supply we have minus 90. So there's something clearly wrong. If the problem was a short circuit transistor here, then you would expect probably that only one channel of the stereo amplifier would be faulty, because this is one channel. We have exactly the same for left and right channels, and ours has a fault on both channels. So unless we've got short circuit transistors here on both amplifier channels, which it could have, it's unlikely that's the problem. There could be something wrong in this drive circuitry so that this transistor has been switched on permanently. It's on and stays on. But again, you'd have the same problem on both channels, and we have a problem that appears to affect both channels, yeah? And having two faults the same on each channel is a little bit odd, yeah? Unless our by chance circuitry effectively switches the power on both channels between 45 and 90. But that seems a bit strange to me. Why would you do that if maybe one channel isn't being driven? Yeah, was only got the quiet bits on. I don't know, but it seems wrong to me. So it might be we've got something wrong with the power supply, or there's something wrong with this switching. But that basically is why I can see a plus 45 and a minus 90. And this is why the protection lights are on, because the protection lights, basically the protection circuit, monitors the voltage here. And the voltage here should be around about 0. Yeah, it shouldn't be off one direction or another, because if it is, it puts a DC voltage across the speaker, which will burn out the speaker coil. The speaker is an inductor, it's a coil. And when you're passing an AC signal through it, it has reactance, it has inductance, yeah. But when you're passing DC through it, it's much more like a short. It will still read a resistance, but basically a DC voltage here will burn the speaker out. So your protection circuit basically monitors these voltages to make sure they're balanced. It monitors the voltage here to make sure it's around 0 when there's no input. So that is the theory, and I think there's enough there for you to understand roughly where we need to look at our amplifier to see what the problem is. So the next thing I'm going to do is try to identify all the voltages, plus 90, plus 45, minus 90, to measure the voltage here, and obviously check these transistors and see if I can see where the problem is. Okay, let's test resistances first. Let's have a look around this. So it looks like, although I haven't checked, that these three transistors are probably the output positive side for one of the amplifier channels, and these are the negative. We know this is all positive voltage, so this is almost certainly one amplifier channel that we can see here. And then we have another set of three, three of these. It looks kind of symmetrical, yeah. So this, I would say, is the other amplifier channel. There are two of these larger transistors or MOSFETs here, and there are also two of them there. So I'm guessing these are the switching between the two voltage supplies. And then we have some sort of driver transistors there too. There's three on this side. Actually, it's slightly different. Okay, and then we have two there, and we have three there. Okay, so this is all kind of symmetrical, if you like. Let's have a look at what we've got. So first of all, these are probably doing the switch. I'm just going to look for shorts. There's no short. I'm on continuity. No short here. This might be a MOSFET. I'll just get the part number. One moment. It's IFPFZHDO. That sounds like a MOSFET. Let's have a quick look. Yes, it is a MOSFET. So we can just say that our diagram when I drew, as I said, could be transistors or MOSFETs. So I'll just show you that. Here we have it. So in our case, this is actually not a transistor, it's actually a MOSFET. But the principle is the same. IFPFZHDO. And I've just checked for the ones on the other side, because you'd expect these to be P-channel MOSFETs, because these are PNP transistors, and in fact they are. This one is IFP150N, and that is a P-channel MOSFET. So that's it. These are transistors, by the way. These are quite a common types. These are these are C5240, and the other ones will be the PNP ones, A1962. Okay, so we basically know what we have there. On our amplifier, we have one of these for the positive and one for the negative on each channel, so there's 4 in total, and these is actually 3 in parallel, yeah, to give more current. So we've got 4 lots of 3 in parallel, and we can see it now, yeah, 3 and 3, 1 of each, yeah, 3 and 3, 1 of each. So that's what we have. There's no shorts around here. Let's have a look a bit further, because this is the side that was really strange. Move my phone one moment. No shorts there. Meter's working. No shorts there, so there's no problem around those. Probe's a little bit loose. Okay, so there's no shorts there. Let's look on the actual output now. So this is the base. Okay, there's no shorts. I go on to diode mode. Okay, and there's no short there. So there appears to be no shorts on the output stages. Okay, but this side seems to be the one that's working correctly. Yeah. Nothing wrong here that I can see. Let's have a look. Yeah, they're reading the same. So this side, MPN. No short. Okay. No, that's the switching transistor. Okay, keep going. So there's no short circuits, but there again you would expect that, because is that really different? No, it reads the same. 2000. I'm just going from collector to emitter. Something reads odd on this one, yeah. So I'm going negative to the collector. To compare with this, I'd have to go to positive to the collector. Okay. So I'm reading something unusual around that set. So on this side here, they all basically, if we check collector to emitter, reads quite high. This is with a positive of the collector, which is the way it would normally be in circuit, because this is the positive supply. Positive to collector. And these all read, sorry, that one. basically the same on both channels, yeah. They read all basically the same. Yeah. On this side, this is the negative end, so the negative black probe will go to the collector. And that reads like a diode, yeah. That reads like a diode. Same on that one. And on this lot, these read high. The same as those do. So there's a problem on this channel somewhere that's causing these readings, and it's not as short, it reads like a diode. Yeah. That reads the same. Bear in mind they're complementary, so I'm having to reverse the polarity of the poles to make a comparison. Okay. They all read the same. Yeah. So the problem seems to be around here. We'll have to take the amplifier board out and have a look to see where the difference is. Just before I do take this apart, I'll just show you, because we know it does effectively switch on without anything drastic happening. I just want to check and show you that all the voltage rails we've just been discussed are actually present on this. So we'll just switch it on, and they should all come in on here. So this is the power coming into the main amplifier. So if we just go onto the chassis, which is ground, we should have what we expect. So that's 91 volts positive, okay, that's a 90 volt supply. That's a 45 volt positive, so we have both of those. That's ground, basically. That's ground, basically. That's the 45 volt negative, and that's the 91 volt negative. So we know that the way we were looking at this circuit is basically correct, and we have the two sets of positive and negative, 45 and 91 volts. It's sometime later and these have arrived in the post. So we can probably fix this with a bit of luck. I've had a bit of something of a cold, been ill for 4 or 5 days, so my voice isn't back properly yet, so you can just have a laugh at it, or you could even get a comment and say, hey Rich, get well soon, yeah. But I suspect most of it just be laughing. That's the way it is. So I've ordered some transistors. These came from France. I could get them from AliExpress, but they were going to take a long time. And these actually came as a pair. So you get the C4370, which is the NPN, and the A1659. And there's two pairs. Now, on the board here, that's what we actually have. So these are the ones that I removed, the faulty ones, and these are the C4370, which is what I have here. So it might be, and it probably should be really, that these transistors are like matched pairs if they've been sold like this. So let's have a look. And by matched I mean they should be of a similar gain. And what I think I will do is remove the NPN transistors as well, the C2SCs, and I'll change them, I'll fit the pairs. Just good practice really, I think. But I'm interested to see whether or not these transistors have basically the same sort of gain. And I can also compare them with the ones I took out, if I can still find them. Well, that's 145. That's one of the NPN. When I say if I can still find them, I mean I can't actually, because it was short, yeah. We're catching up with where I was. So I can compare them with the C2SC transistors that are in here. So this is the other one, the NPN. They're obviously better transistor analyzers than this. If you're doing a lot of audio repair, it's probably worth getting one, but I think for what I do, the amount I do, this is probably okay, unless somebody tells me otherwise. Yeah, that's very similar, 144, 145. They match the PNP. I'm thinking probably they should, but I mean I don't know if that is actually going to be the case. Let's have a look. PNP. Yeah, 174. It's not a million miles away, is it? I mean, you couldn't say it's the same, is it? A million miles away. Or perhaps that is a million miles. Okay, let's put this one in. And I do think these are related to switching the voltage. Actually, no, these are probably the drivers for the output stage, actually. And because they're short, effectively, that's why the voltage is wrong, because the circuit that detects whether we need the higher voltage, you know, for the size of the waveform, the short effectively just fooled that circuitry. So let's have a look. Press the wrong button. I'm not 100% guys, I'm only firing on 3 out of 4 cylinders. 173. So we can say the two PNPs are basically the same as each other, and the two NPNs are basically the same as each other. So I will replace the two shorted ones. I'll replace the other two as well, as a matter of course. And let's see if this actually now works. I've replaced the transistor pairs then. Just out of interest, by the way, because I've just used it, I bought a roll of this mechanic solder from AliExpress, 0.6mm. This is a 150 gram roll, and this is another lead free solder. So this one is in fact 37% lead, 63% tin, so it's not quite a 60/40, but it seems to work nice. Yeah, it gives nice clean soldering on there. So these are the two I took out, the NPNs, which are actually good. I'm just interested to see how the gain of these compares to the two that I fitted, which I think were about 147. Yeah, it's a bit higher. Actually, funny enough, that's closer to the PNP. Possibly a better match. Okay. Yeah, they actually match better to the PNP ones than the ones they sent with them. I've changed them now, we can always put them back in. So this is the result of the soldering. Nice joints, quite happy with that. So if you're looking for some solder, yeah, this is best enough tried so far from AliExpress. I've just put the screws in just loose, just to make sure that all the transistors will actually fit, because if you've unsoldered them and resoldered them, or you've changed some, it may well be that where the legs have bent, you've got the length of them wrong and they don't line up. So I've got them all in, as I say, loosely, and they do fit. I've also just had a bit of a look around this, because there's a couple of adjustments, one here and one here, and they may be something to do with balancing the channels. Whether we have to, I'm not really sure, or how we would do so. I don't have any information on this, but if anything, I think I'd probably adjust this so that the output voltage when there's no signal is 0. I mean, somebody else probably knows better than me on that, but first of all, let's see what happens. The other obvious thing is this capacitor is gone, and if we look on the other channel, the same capacitor is gone. Whether this is related to the blown transistors, I don't know, but what I have noted is that there's a pair here and the capacitors between them, and a pair here and the capacitors between them, and this may again be something to do with the driver or pre-driver stage. So clearly we're going to have to change these two capacitors as well. All the others look visibly okay, doesn't necessarily mean they are okay, but for now I think I will just change the two that were bad, and then let's see if the actual protect mode has gone off. I've just put the screws in loosely for now, but they're all just in place. So there's a couple of precautions we should take with this before we power it up, really. One is that these transistors with the metal tabs which are connected to the center pin, just get the thing on bleep. Yeah, you can hear it bleeping, yeah. They shouldn't be connected to the heatsink, or at least only one side should be, if you see what I mean. So, just want to make sure that, yeah, this is isolated. This is isolated. I do have a connection to the heatsink, you can hear the bleep. So I just want to make sure that they're not shorting to it. Do have like little insulation washers underneath, or maybe it's just the design of these. They're not. Yeah, the tab is connected. So yeah, there's no short there. Yeah, we need to make sure on all of them, just to make sure that we're not connecting. These are just plastics. I don't think they would connect anyway, but no harm in trying. Okay. Same on this side. Because if you have a short from any of these to the heatsink, it's going to go bang. Or it would go bang if we weren't taking the other precaution which we're going to take. So the other one is that we're going to power this up via the light bulb. Okay, so we can test it. Now at least we can test it safely. In the case with this amplifier, the heatsink is actually bolted directly to the chassis, so effectively the heatsink is ground, 0 volts. All the metal tabs on these transistors will be at minus 45 or 90 volts, depending on how it's switching it, and all the metal tabs here will be on plus 45 or 90 volts. So this is why we have to be sure we don't have any short circuits from the tab to the heatsink, and that be because the little mica washer underneath has come away or it's gone missing. Usually it's like a little see-through washer, don't lose them. When I say washer, they're kind of like square with a hole in. Yeah, I'll show you one. Yeah, these sort of things, they vary in size. These are probably for this type of transistor. So usually embedded in the heatsink compound is one of these. Don't lose them, yeah, and make sure they haven't gone astray. Sometimes you may find this sort of thing where the actual heatsink is insulated from the actual metal case, so it doesn't touch the metal case anywhere, and it has like some sort of plastic mounts to hold it away from it, so it's insulated. And in that case, sometimes you may find that there's only mica washers on either the positive or the negative side to insulate the transistors from the heatsink. In that case, the metal chassis is ground. The heatsink will be at plus or minus 45 or 90, but it's insulated from the case. And depending on which set of transistors has no mica washer under it, be the heatsink at plus or minus whatever the voltage is. So that is actually quite normal sometimes for one side to be connected, but not both. Okay, so just bear that in mind. It varies a little bit on the design of the amplifier. So this is the light bulb. That's switched to limit, so the power's coming through the light bulb. Just double check that. Yeah, it is. So I'll switch this on now. I've got no input connected to it, no speakers connected to it. I just want to see what it does and I power it up. These are the protect lights, the two of them here, and the power lights. So let's see what it actually does. Well, it went on bright, then it went dim. I'm not happy with that. It seems to be drawing quite a bit of power. It may just be going dimmer and dimmer. Yeah, it's on, but the protect light is on. Okay. Obviously the capacitors have charged up or something like that, so it's not got a short in it, but the protect lights are still on. It may just be the current limiter making it do that, but let's have another go. Let's see. Yeah, bright and then dim. Protect lights are on. Okay, it didn't go bang or anything like that previously with the protect lights, so let's just try it and see what it does. Protect lights are on, so that's without the light bulb in the circuit. So once again, I think we need to have a look at the voltages around this amplifier, because there's obviously something else still wrong with it. Let's look then at the main voltages we have in this. So I'll just power it up. fans are running. What have we got now? So this is plus 45 and this is minus 45, so that's correct now. 45 on this channel. Well, let's see if we can figure out what's wrong with this still. So we'll switch it back on again, directly on the mains, because nothing bad happens basically. It's just untangle my meter wires a moment. Okay, so from ground, let's check the power rails. So we have, this should be the plus 45, yeah. Oops, slipped. Don't go slipping. Plus 45, that's okay. What's on here? Plus 45. Let's have a look at the negative rail. Is this still reading 90? No, it's reading minus 45. How about the other channel? Minus 45. So the power rails are balanced now. So the other reason the protect light would come on, mainly, unless there's some problem with the protection circuit, is if the output is wrong. So with no audio input coming into it, no input coming in, yeah, the output should be basically 0. So the output is coming through these low value resistors off the emitters here and here. So let's have a look. So that's like, yeah, 0.16. It should all be the same because they're all connected together. 0.165, 165. So that's near to 0. If we measure the other end, it reads practically the same. So there's basically no current flowing through there, or very little. What about the other channel? So this should be the same. Oh no, this is 21 volts. And that'll be on both sides. Okay? So, let's go to the other side of the resistor. 21.4. 21.4. So there's basically no current flowing. That's because it's in protect mode, so the relays are open and there's no speakers. The whole idea of the protect mode is to stop that voltage going straight through your 8 ohm speaker to ground, causing a lot of current to flow, possibly destroying the speaker, damaging the amplifier more. So something's making this side turn on. We can see this on the emitters. So the emitter's connected to the resistor. Yeah, we can go to the emitter, we can go to the emitter. So on the base, 8. So look at the other channel. 0. So you can see clearly that something's putting a voltage on the base here. 8 volts. The emitter is 21. So the base is actually below the emitter. Okay. So on these ones, 20 volts, 0 volts. So 0 volts on the base here, 0 volts on the base here, 20.1 is on the emitter, 21.3, 20.4. So those are turned on, I would say, because the base is a little bit lower than the emitter, and these are PNP transistors, I think, so I remember. Base here is 7 point. Oh, I've got a bad ear. Let me get a good connection. Right. 8 volts. 21. So the base is below the emitter, and these are NPN transistors, so they are off. This side, 20. Base, 21.3 on the emitter. So the base is below the emitter, but this is a negative rail. There's something wrong anyway in this channel. Somewhere there's something wrong here. So it's like it's not balanced. The transistor is being switched on by something further back. Obviously a schematic would help, but we know there's a problem in there. Now basically I'll just switch it off a little while. We can talk about it. We have two effectively identical channels, and yet there's something wrong with this amplifier, yeah, compared to this amplifier. So obviously schematic would be useful. I don't have one. Maybe I can get one. Let me switch that other camera off. Get rid of my doppelganger from over there. Just see if anything's getting warm. Maybe a little bit of warmth somewhere near. I think for ease of repair, maybe the first thing I'll do is try the thermal camera. So let's get the thermal camera and let's have a look to see if we can spot something on this amplifier channel that's getting hot that isn't on this one, and hope we can. I'll show you what I do see then. So we have this group of components here with like 2 power transistors and a whole bunch of them, and the pattern of these is basically the same as this pattern, the same number of transistors, the same number of power transistors. So if we look here, you can probably see there's like a whole bunch of components there, and they're all pretty warm. And you can see the transistors, there's 2 to this side which are a bit cooler than the others, but that's basically what you can see there, yeah. And then one of the power transistors is effectively hot, and the other one is cold, by the looks of it. Yeah, just trying to look where the other one is, but it's one hot one, and the other one's there, it's like purple, it's not lighting up at all, okay? It's kind of here. If you look at this channel, we have a different pattern. So the transistors, if you look at them, you see what's warm on that one compared to what's warm on this one. The pattern is very different. That's that little cluster. That's that little cluster. And then on this one, the 2 large power transistors, both of them are cold. Yeah, I think you can see one's actually here and one's actually here. So there's something different in that little clump of components. So the strange thing here really is, this channel appears to have the wrong voltages on it. Yeah, it does have the wrong voltages on it. But they're both those power transistors that effectively here. They're probably a bit hard to see, but they're here on the screen, here and here. They're cold, yeah. But if we go to this one, this channel appears to be working. But one of those power transistors is at like 68 degrees and the other one is, well, 31. Compared with 29, compared with 27. So in actual fact, this appears to have a problem. Look, it's 70 degrees now. That can't be null. Yeah, 71 degrees. So let's take this out and have a look. This is the transistor that was getting hot. Let's just see if we can remove it. We might have to add some leaded solder, actually. Yeah, that's going to help a little bit, get a bit of leaded solder on it. But I wouldn't be surprised to find this transistor is actually okay, and it's something around here or something else. And what also does puzzle me, guys, is why this one is getting really looks like too hot, and yet this channel, the output's really okay. Well, they're not okay, but there's no offset, DC offset. I mean, it could be okay, yeah. There's no DC offset on the output. And the other channel has a big DC offset, but those transistors are not getting hot, which makes me think I may have different faults on each channel here in actual fact. So, let's have a look. This is another one of these A1659 transistors. I actually have one more, that's all I have. Let's have a quick look on diode test mode, but then we can always use the analyzer. Let's just have a quick look. I wouldn't be surprised this is okay. So it's a PNP, so negative to the base. That doesn't surprise me. We'll get the analyzer to be sure, but that looks good to me. Okay. PNP silicon transistor, gains as good as the other ones, that's fine. And I did say I thought that would actually be working, so that isn't faulty. These things are not exactly symmetrical if you look at it. There are some differences. It's not like there's 2 symmetrical channels here exactly. I think now I really will try to find a schematic for this to see if that will help us to fix it. Well guys, obviously that transistor getting hot isn't actually faulty, but there's something else wrong with this. But there's a few things about this that don't make sense to me. I'm going to measure another voltage in particular, just to be sure that I'm correct. And then let's put this on a piece of paper, but this whole problem is saying two different things to me at least. Let's just make a few more measurements, follow with me, and then we'll have a good chat about what's going on, or what might be going on. There's something that really doesn't make sense about this to me. I'm going to show you. I've put this on paper as well, so I can show you in a minute on the paper, but just bear with me. Right, okay. So we'll go on this channel first, okay? Base is 0. Collector plus 45. Emitter, well, yeah, almost 0. Base 0. Collector minus 45. Emitter, well, yeah, almost 0. This amplifier channel lights to protect light, because both lights are on, which tells me there's a problem on both channels, unless there's some problem in the detect circuitry itself and the phantom faults. But that's what it's saying, yeah, bear with me. On an amplifier, and it's quiescent like this, you shouldn't have 0 on the base. You should have like a little bit less than plus 0.6 with comparison to the emitter on here, and more or less close to minus 0.6 on the base with respect to the emitter here, because the transistor is supposed to be almost switched on. That's the first thing. So there's something wrong with this. We know this transistor here is getting hot, but it's not faulty. There's definitely something wrong on this channel. Now look at the other one, and this is even stranger. NPN transistor, base is 8 volts. 45 volt supply, positive. Emitter is 21. Now, the base at 8 is lower than the emitter, which is 21. It's like 13 volts lower than the emitter. So this transistor should be switched off. And yet for a positive voltage to get through to the emitter, it says the transistor switched on, but it can't be switched on. Yeah. Look at the PNP ones. Base. Let's get on to a good connection. 20.3. Yeah. Emitter. 21.25. That has more than 0.7 volts. Has more than 1 volt, I think, or about 1 volt across the base emitter, negative. It shouldn't be able to support 1 volt. That would say the base emitter is open circuit, but they're not, because I've looked at them. Yeah, they're not. Right, this is the weird thing. If I'm seeing 7.898 here, and I'm seeing 21 volts here, what will be the voltage if I measure from the base to the emitter? Yeah, well, it's 21 minus 8. Yeah, 13. Do you want to know what's here? Look. Emitter. Base. Nothing. There is no voltage difference between the base emitter. But if we go to ground, and I was on ground, I mean, there's lots of grounds on here. I can go to a ground on here. Another ground. If I measure them, 8. 21. So they're reading different, so there's a voltage difference. But is there a voltage difference? Well, there isn't, is there? We just proved it. None. So that transistor's turned off. So where's the 21 volts coming from? Look on the PNP side, yeah. Same sort of thing. Go to ground. It's the 8th pin up on the axis ground. 1, 2, 3, 4, 5, 8 ground. Hand out of the way of the meter. Go on this one. 21. 20.4. Yeah. What's the voltage across the base emitter? Well, the base is about 1 volt less than the emitter. Yeah. Base. The wires at the fans. 0.2. So that doesn't make any sense. I mean, how can we have completely different voltages with reference to 0 volts, but when you measure across the 2 points, they're, practically the same voltage? Does that tell you something wrong with my test meter? Well, we can soon prove that, can't we? Here's the little an end meter with a different set of leads. Yeah, let's have a look. Volts. Let's see what it says. Let's just put it somewhere where we can see it. I think you can see that. Okay. Different meter, different test leads. Power on. I can use the same ground, I can use the chassis grounds, use the same one. I can prove this is the same ground because if I measure the voltage from ground to here, it's minus 45, and if I measure from chassis to the same place, it's minus 45, yeah. Well, we'll go from the chassis this time, don't we? Don't mind. So, what have we got on the base? 7.88. Emitter 21. What's the voltage between the base and the emitter? 0. That's a paradox, yeah. That's a paradox. Not only can I not fix it, I can't even figure out how the voltages can measure like that. But, well, the only real reason to that, actually, is that the emitter is nowhere near to actually being on ground, which it won't be because the relays are open, so that emitter effectively is floating. And I think that's what's causing the strange readings, but it doesn't quite explain why the base... this is something to do with floating voltages, I think, but it's not helping me to fix it, yeah? I did say I'd put this onto a piece of paper, but I think it was clear enough. So the markings in the blue pen, 0 on the NPN base, 0 on the PNP base, 0.165. Point of that channel is surely those transistors should be almost biased on. 2. These voltages, well, they don't make sense, do they? They don't make sense. This transistor apparently is more on than it could be, but when you measure across the emitter base, it isn't. Yeah, same with that one. Something really seriously weird about this. But I've got to fix it, yeah? Well, I've got a next step we can take. Guys, I have a schematic and this is the next step. So this is thanks to one of the guys on Badcaps forum. I was asking if anybody had a schematic and somebody posted me this one up. It's under a different file name, but I think it is actually the correct schematic. It just says TXM amp BD. That's all it says. So it's not exactly the same, well, the full model number, but I think this is actually the correct amplifier. Because there are some interesting traits that make it look correct. First one is these connections, the 14-way and the 9-way, which is what we have. I was using this point to pin 8 as ground when I was actually making those voltages. That's how I actually knew where the ground was. And what we're seeing, basically, if we look at the schematic, is quite similar to what I thought it was. So, this is your main amplifier output. This is the NPN side, yeah, NPN transistors, and these are the PNP. These are all those emitter resistors, and there's 3 output devices in parallel, 1, 2, 3. Okay. This bit of circuitry, this is what's switching between the 45 volts rail and the 90 volt rail. Okay. Pretty much as we described, it's being switched by these transistors, and they're picking up some sort of drive from the output. So without me really going into exactly, this arrangement is kind of like some sort of a comparator type circuit with transistors, and it's effectively monitoring the voltage on here. Can you see that? So this is the junction of all the emitter resistors. Inductor, this is your relay, okay, and this connects to your speaker output there, and this other channel to there, okay. And it's why that you can have both speakers connected to one connector, or you can have one on one and one on the other. And that matches the way the speaker connector is actually wired up, the speak-on sockets, okay? So this bit of circuit we can see is monitoring the voltage on here, and it's switching this on in such a way that when the voltage on the output is getting towards the 45 volts, and that's what I think it's doing, it's comparing 45 here with whatever voltage it sees here. Yeah, and this effectively switches. It's a bit like an op amp, if you like, made of transistors, but I'm pretty sure that's what it does. This circuit's got a name, and I can't remember what it's called because I'm not a circuit builder, but I do basically know how it works. And we have the same on the other side. This is monitoring via a resistor network at the minus 45. It's also monitoring the voltage here, and when it goes negative, gets close to 45, it switches this on, and this puts the 90 volt rail here. The transistors we had short, I'll have a look, but I'm guessing they're in this circuit. Let me have a quick look. Okay, actually I'm wrong. The transistors we had short were this one. Okay, and this one, and these are actually driving the output transistors on the negative side there. Okay, and there, that's where the fault was. Let's have a quick look how this thing actually works now. I'm not going to go through the whole thing, so at this point probably don't need to, and we'll just look at one channel because the other channel is the same, apart from the fact it's got a different fault apparently. So we have input somewhere here, signal. We have signal 1, SG1. Not Stargate, by the way. So signal comes in via a capacitor, and it comes into this circuit and this circuit. Yeah, these two, here and here. Base of both these transistors. One's NPN, one's PNP, so effectively as it goes positive waveform, it turns this one more on. As it goes negative, it turns this one more on. I think the other pair is again some sort of comparator to do with feedback. I'm not too bothered about them. Let's just follow the signal path in, yeah, and let's just follow the positive half cycle first. So signal comes in, positive half cycle, switches this transistor on, which drives this transistor. Okay, that then drives this transistor, which is the pre-driver, and these are your output stages. Okay, so the amplifier itself, effectively, positive half is that one, this one, and these 4 stages, yeah, of amplification. All the rest of them are to do with compensation and feedback and stuff like that. Yeah. Same for the negative half cycle. This one, which drives this one, which drives this one, which is the driver, the one that was short, and the output stages. So again, 4, yeah, and exactly the same on the other channel. They're identical channels. Okay, so that's the path of the amplification. That's the signal path coming through, and we can use that to trace. So we can put a sine wave into the input, and we can see where it goes. Okay, all the rest of the transistors we see here, as I say, are either to do with feedback, or they're to do with monitoring the output, okay, and to do with switching the voltage rails. This little bit of a circuit up here is quite obvious because it says phantom, which is really phantom. This is the 90 volt positive, and this is where we saw 90 volts DC on the fuse. And if you look, the 90 volt comes in here, and this effectively is a voltage regulator. So it's dropping the voltage through here, and that voltage actually goes to the plus 48. That's the phantom voltage for microphones, condenser microphones. So that's what that circuit's doing, and what the fuse with the 90 volts DC is actually part of the supply, the phantom 48 volts. This little thing I think is just not there, and this little thing is just not there. There seems to be a whole block, yeah, saying do not use in TXM, so those things are just not there. Whatever they do, I don't care, because they ain't there. Looks like some sort of clip sensing or something. So that's how it works, guys. What I think is happening, this is just more supposition from me, because some of you are probably going to shout out the screen and tell me what's wrong with this. But if there's some sort of problem with this base drive circuit here, I mean, we've changed that transistor because that was short, but this is the complementary, the positive one. I actually changed it. I changed the pairs. I changed it. But I'm wondering if there's something wrong here, so that this voltage rail here, the base, is effectively floating. It's floating, although there's a diode that should hold it. No, it doesn't hold it to ground, it goes down there. If this is somehow floating, that might expect why I get these weird voltages on the base that don't really exist. Okay? And the same on the negative half. Exactly the same on the negative half. But I don't think it's those transistors. I've changed the transistors. The one that's getting hot on the other amplifier, I'll just tell you which one it is on the other amplifier channel. It's Q118. Where's that? Well, it's here. So the one that's getting hot is effectively in the drive circuit. Into here. That feeds, well, there's another transistor down here. I wonder if some of these transistors might be short, although I did effectively have a look around a long time ago. I think what we should do with this now, guys, we could put a signal in and see how it goes. But I think it might make sense to kind of start at the beginning and just measure a few voltages, just following through the 4 stages of the amplifier and both half, and see if we can see anything with the voltmeter. Otherwise, if that doesn't give us anything conclusive, then we're going to start using the oscilloscope. Let's have a look at this floating rail that we seem to have. So I'll just go on resistance range. That's from this emitter rail of this amplifier, the one that has 0 volts on. And we'll go on to this one. Do we see any difference? Well, yeah, that appears to be open. And that has some resistance, yeah. So this is why it's floating. And this is reading, towards a meg, but it's actually dropping. Okay. So there's a difference there. So let's have a look on the schematic to see where something might be open circuit. Because effectively, this seems to have an open circuit from the emitter resistance to ground, and this is high resistance. You would expect it to be a high resistance. Okay, but you expect to find something there. So this line effectively is the output from the amplifier, or the emitter resistors that goes through the relay to the speaker. And the relay is open at the moment. This is the protection circuit, basically. So is there any paths to ground we can see? Well, there isn't one here because there's a capacitor. So from here to ground, that capacitor would read open, not that way. The switch on the relay is off, so it can't be going that way. Some going down here. Oh, there goes to a 23k. Oh, and that goes to ground. So we have two 22k resistors here from the output of this amplifier. We have 2 more here from the output from the other amplifier, which connect to this transistor, and then we have 22k to ground. So yeah, through there we should read 66k basically. So it could be I'm reading through here, and maybe the resistors on the other channel are actually open circuit. Is there anywhere else? Well, I'm using resistance mode, so I shouldn't be switching any semiconductor junctions on, so I don't see any path via these ways. Diodes, transistors. Yeah, I don't really see any obvious path to ground there. So let's have a look at these resistors and see if maybe we've got an open circuit resistor, either 284 285 or 184 185, and then we have resistor 22. That's common to both. Sorry, resistor 3. That's common to both, so I can't see that being open. It's going to be either this one or this one, 284 285, or it's going to be 184 185. Let's check that out. I might be getting somewhere now, guys. So these are resistors 184 and 185. They're here, and that's the transistor Q5, and the emitter is the one that goes to the 20k resistor basically. And it's just reading now, it's just auto ranging, but I'm sure it's going to go somewhere. Well, obviously something else is in parallel with it's reading lower, but we can check. So this is the emitter of Q5, and then we have the resistors 184, 185. Yeah, the transistor connects to one of them, which is 22K, which reads all right, which goes to the other one, which I think is here. Yeah, and then the other end is over here somewhere. Yeah, so they read basically okay. So I know that isn't the problem. Now, I was trying to find the other resistors, 284 and 285, and I couldn't find them anywhere. I'm sure they're here somewhere, but I got distracted while I was looking. So I couldn't see this. I bet you could see this on the overhead camera, because the angle I'm sitting at, I'll show you this because you'll have to believe me. The angle I'm sitting at in my line of sight, like that, yeah? What I can't see is what's behind this. And for that matter, I can't see what's behind these resistors, yeah? Maybe I could have seen that problem. And this is where obviously I failed in my visual examination, because I couldn't see behind. Let's move these wires. There. Yeah, I bet you could see it before in the overhead. Some of you probably been shouting this out, but hey, I found it. Yeah. So this is a resistor, and it's open circuit. Yeah, I think that's a bit open circuit, that one, guys. What do you reckon? I could use the multimeter, but I think that is open circuit, that one. There's R267. Was there another marking under here? Let's have a look. See what the resistor is. Get this bit of glue off here. And this is the amplifier channel that's got the weird thing going on with the voltages and something floating. And it's definitely open now. Can we lift this stuff up? What's it say? Very glued on, that is, guys. It is a resistor marking or something. Let's get some more of it off. Well, I've got the chewing gum. It's like bloody set chewing gum. Far enough out of the way to see this is R244. Yeah, you can see it. That's R244. That's open circuit, yeah. Now the transistor, I'll bet's connected to that. Wouldn't surprise me. See it there with the lid missing, chunk missing. Q221. So let's have a look for R224 and Q221 and our schematic, and see if it's in any way related to that voltage that was floating. Okay, so I'll just zoom in a little bit. This is the resistor that is actually blown, this one. So this goes between the driver, or pre-driver. We'll call this the driver. This is the driver. These are the output devices. So this is the NPN driver via a diode, via the resistor, which is blown open circuit, and then via the PNP driver. So this end connects to the negative voltage rail. I think we had 90 on it originally. We fixed one problem. This goes to the positive voltage rail, and the current is obviously flowing through this transistor, through the diode, through this resistor, and blown it, and through this transistor. Now I've already changed the two transistors. Although the NPN one's tested okay on both on the channel, I've changed them. Yeah, I've changed them both. So that I have done. I'll need to test this diode 1M4148. I've got some. I'm not sure I have a 68 ohm 2 watt resistor. So that's that damaged. The other thing that blew is the transistor. Now the transistor is blown is this one. Okay. So, well, this is the one that went short. Oh yeah, collector base was short, straight through the diode, straight through the transistor to ground. So we can pretty much say that going short blew this one. That's fairly obvious, okay? I need to test then this diode, because the current went through the diode. I need to test the other diode. So let me test those two diodes, and let me see what this transistor is, and do I actually have any. I have the meter on diode mode, okay? So the two diodes, D210 is here, and that reads okay actually. Yeah, and 212 is here. Ah, that one's short. Okay, so that one went short, 212. So we need to change that diode. And this transistor, well, I think it's an open circuit is the best description of that. Yeah, but it has a part number on it. So let's see if have I got those, have I got the resistor, I know I've got the diodes. Actually, I made a slight error in that, but it didn't really affect what I was saying or make it wrong. It's the other transistor that went short. It wasn't this one, it was this one. So this is the NPN driver transistor, this is the PNP. And on one of the channels, this went completely short circuit, all three terminals. This is the transistor that blew the lid off on the same channel that has went completely short. This diode is actually reading short. This diode reads okay. This is blown up, so short, blown. Current went down through this one, through another diode and into the transistor that was short. So what I'm going to do now is I'm going to test this transistor, the PNP. So that was Q221, this is 222. I'm going to test the diodes 213 and 211 and see if I see any damage around here. And after that, I'm going to go on to the other channel in the same area and do the same thing, although this failed in a different way. I think this one just went short base emitter. Okay, so on this side, this is the transistor. Now this is a PNP, so it's going to be black onto the base. So that's a diode junction. That's a diode junction. It's open collector emitters. That probably looks all right. This is one of the two diodes on this side, and that reads okay, and this is the other one. So that part reads okay. What I'm going to do now is look at the same two transistors on the other channel, and I'll let you know if I find any problems there. Here's transistor Q121. Now this is an NPN. This is the base, pretty sure. So that reads okay junction, okay, collector emitter, yeah, it reads open, and then we have the diodes, there's three in the area. This is one of them, this is D114, that was D110, this is D112, and that all reads okay. And then we just look at the PNP side of this amplifier channel, so that's over here. This is the PNP, so this should be negative on the base. Yeah, not in the way, it's okay. Negative. I think it might be the other end actually, it's the other way up. Let's have a look. Yeah, that reads okay. Reads okay. So that looks alright. And then the diodes. That one and the other one is here. 113. It's just slightly off the shot. The other one's here. So they all read okay. So we're really down to this blown up transistor, the 68 ohm resistor and some diodes. Well, the good news is I have some of the transistors. They're poles, but they read okay. That we can replace. Let's have a look. I have 4 of them, so I have a few chances. Have a look. Yeah. Nice gain. That's a good one. I'm fine with that. I have a few more. So I have transistors. I have the diodes. What I don't have is the 68 ohm 2-watt resistors or anything similar I could put together. So obviously I need to order this resistor and the transistors I have, but that problem, although it's obviously a problem, doesn't really explain why we had this floating voltage on the base and emitters of these transistors. So I think there's probably still something else wrong with this. So let's have another look at the schematic and see if we can figure that out again. This is the actual schematic. I've printed it out because it's a little bit easier to show you, because I'll show you the PCB at the same time. But basically, to recap, I actually made an error. And this is before I had the schematic. So we knew this transistor was short on both channels, and I changed them. And I said at the time, well, I might as well change the NPN ones, which I assumed were these ones, next to it. But I didn't think it through properly, because this is the heatsink. It says here, heatsink. And this is the NPN, the positive half of the output stage, the driver, the negative half, and the driver. And it makes sense that that transistor is on the other side of the amplifier, the NPN half, the positive half. What I actually changed was this one. So this transistor is the same type as this one, but it's sitting next to that one. And both of them, for both channels, are sitting on the same side of the heatsink. That's why there's extra transistors on one side. I said I've got 3 on one side and 2 on the other, and I couldn't really figure out why. That's why. So what I haven't checked is this transistor, okay? Also, this transistor is the one that's getting hot on the other channel, but they're both cold on this one. So there's a bit of a tie-in as well with what's going on with the other channel, but let's stick with this one for now. Let's have a look at this transistor. There's another reason I'm interested in this. We've got something going on with floating base voltages on this amplifier as well, possibly on the positive half because there's a positive voltage on the emitter, and that's also the base here, also connected to this transistor. So there's a lot of reasons to look at this and make sure this transistor is good on both channels, but we'll do this one first. I have my meter on diode mode, and the transistor is here. So this is the NPN side. Effectively, this is the complement of the shorted PNP on the other side. So is it good? So base, collector. Well, that should read like a diode junction. It's not. Base emitter, not. Collector emitter. This is short. This is next to the other transistor that blew up on the 68 ohm resistor. I think they're all in this part of the circuit. So that is short. While we're at it, let's look at the same transistor on the other channel. Okay. So this is the same transistor on the other channel. Base collector. That reads like you'd expect, a diode junction. Base emitter. And this one isn't short, okay? So we have a short circuit on collector emitter on this one. Now this raises it. Sorry guys, the voice is getting worse, but we've got to fix this. So this raises an interesting point now. This transistor is short collector emitter. This end is connected to the plus 90 volts. The other end is connected via some resistors, 4.7 ohms it says, to the base of the output transistors. But we know on here we were only seeing about 8 volts, and if that's short, then surely you would see 90 volts on here, unless the track or these resistors are open circuit. So we better check these, and I'll check them on all the channels. And while I'm at it, on the PNP side we've got the same sort of setup, and we know this transistor was faulty. So I'm now going to check the continuity from the emitters of these driver transistors to the base, and if I don't see continuity, I'm going to check these resistors. So guys, this is the transistor that was short. Okay, and the emitter should go to the base of all the transistors, and it doesn't, as I suspected. The complementary of this one, this is the NPN, the PNP is actually here, and that's the transistor that I thought that was this one, and I changed. Okay, let's look at this one. So we go to the emitter. Well, that reads okay. We have a connection to the base here. Let's get on with the other channel. So on this one, this is the transistor that reads okay, NPN. And this is the base of all the transistors. So we're going to have a continuity. And then on this side, this is the PNP. That is the one I changed thinking it was this one on the before I had the schematic, obviously. It looks like this channel has got all the base resistors on the output stage open on the positive side, and this has it on the negative side. So the base resistors are actually down here. You can see 1, 2, 3, 4, 5, the 6 of them, okay? Now there's only 3 base resistors, one that schematic we were just looking at, which is now here rather smaller. There was 2 lots of resistors, so there was effectively the base resistor and another one connected into the emitter circuit, yeah? Hence the 6, and they're probably not all 4.7 ohm. But let's check them. So let's go on a good channel first. We know this one looks like it's good. So, resistor. It's close enough to 4.7. This one, what is it reading? So they are 33 ohm resistors, in fact. This would be another 4.7, I would think. Yeah, it's good enough. 33. Yeah, this would be another 4.7. Yeah, it's close enough. And this will be another 33. Yeah, that's a good channel. So this is the bad negative side on this channel. Yeah, let's have a look. Open. 33. Open. 33. Open. Where's the other 33? Oh, is it this one? Yeah. So open resistors here. I'm sure we're going to find the same on that one. Let's have a look. Open, as they must be, because the voltages we were seeing on that short circuit driver would be 90. Yeah, 33. Open. 33. Oh, another 33. So 33. Where's the other one? How many open ones are there? That one. That one. Should be reading like 3.1k or something. That's what it is. This one. Yeah. So those resistors are all gone. And then this channel we think is good. Well, this side. Yeah. Let's have a look. Yeah, that should be the 4.7. So this is the other good side. There's one more somewhere. I can see where it is. Uh, 4.7. The other one's down here, I think. Yeah. So they read okay on that as well. So we need some resistors. That's the next thing we need. Doesn't explain exactly why this one was getting hot. I think the next thing to do with this now is probably going to be, just to be sure, because I need to order parts. I think these might be 1 watt resistors. They look a bit unusual. They're not like these. These could be 1/4 watt. These could be 1/2 watt. I can have a look. But I think what I'll next do with this is actually, I'm going to take all the transistors off, the small ones in this half, and see if I can see any problem with them. And probably the same in that half as well, because the damage has obviously gone quite a way into the amplifier. So I'll now check the other various devices. It's time consuming, but I think it's probably the best way at this point to see what else is wrong with it. And another good reason for doing it this way, and I'm sure some of you will sympathise with this, it gives my voice a rest a little bit, yeah, rather than trying to talk it all the way through. Okay, let me see if I can find any more damaged semiconductors on this circuit board. In silence. So guys, I've replaced the shorted transistor, I've replaced the shorted diode, I still need the resistor, I don't have anything like those. I've been through all the other transistors on the board. In the end I didn't unsolder them all, but what I decided to do was check for shorts anywhere. Now while I was doing that, I noticed something quite nice about this. It's been staring me in the face, but I'll mention it. So you'll see that the transistors, the symbols on the silk screen, are either like a shape showing where the flat side is, the orientation, and some of them are solid white and some of them aren't. And I thought, well, why is that? And the most obvious reason being that the ones that are solid white will be PNP, and they are. And the ones that aren't are NPN. But the other thing you'll notice, these white dots, yeah, that's the base. So if we go to one of these, we know straight away it's going to be an NPN transistor, yeah, and we know where the base is. So we can go straight away red to base because we know it's NPN. We should go junction, junction, and then there shouldn't be a short between the other two, which there isn't, yeah. So quickly we can just test it. And then these are PNP. So if we do the same thing with the red on the base, we won't find the junction between both legs. Okay. If we go with the black one onto the base, because it's PNP, we get the junction. And negative to the collector. Again, not a junction, just a climbing resistance. So you can very quickly go through knowing whether or not you have all the semiconductor diodes that you should have, because you know the polarity of the transistor and where the base is, yeah? I've also tested all the diodes, so I haven't found any faulty diodes. Basically, I know there are no short circuits around any of the semiconductors on both channels. The other thing I'll just quick mention is these resistors. So these are the base resistors. There's one here, I can weigh it down a bit. Okay, so you can see it's a 4.7 ohm resistor. I don't know the rating of these. According to the schematic, they're nothing special, but they're different from these. So these could be quarter watt, these could be half watt. Also, is it possible these are like low inductance or zero inductance resistors? So a resistor internally has like a metal film track, like a little spiral inside it that effectively gives the resistance. Wire wound have wire wound inside them, but effectively that means the resistor has some inductance. It acts like an inductor because of the coil of either the tracks on these and the metal oxide or the wire. And I know there are carbon resistors that are non-inductive, so they have effectively a solid block of carbon, and the composition of the carbon with various impurities in it sets the resistance. So does anybody happen to know if there's anything special about these resistors, because I need to order some, or can I just well, I haven't got any half watt anyway, so I'd have to buy some half watt, so I need to buy some resistors. And a bit of advice, guys, yeah, please, that would be much appreciated. As well as all the diodes and transistors, another important thing to test are these little trimmer pots. These can and often do fail, and what usually happens is the little wiper, the metal wiper, loses contact with the horseshoe shaped carbon track, so it effectively goes open circuit. Now quite often with these you'll find that one end is actually connected via the PCB track to the wiper effectively. So if you look, you'll see that the wiper and one end on the PCB track are connected together. Okay, the other end is the resistance. Now this one's reading 372, and if I just adjust it, it should change, and we can put it back to how it was. You'll see it's changing, yeah. So that's that one. So it is working, yeah. Let's look at this one. So here it is. Again, one end on the track is actually connected to the wiper directly. Okay, 0 ohms, and the other end, I'll just get onto it and see if I can wedge the probe on there again like I did before. Now she's reading 532. To make sure it actually works and actually adjusts. Well, the fact it's reading over 470 ohms, and this is actually a 470 ohm pot, makes me think there's something wrong with this one. Look. Yeah, this one's got a problem. Can you see that? Yeah, those two pins are connected together on the PCB anyway. Yeah, you see it? It's reading higher. It's reading higher than the value of the pot. Yeah. Okay. So that's something else that we need to change as well. It's quite possible that that caused the original failure. I have some of these in stock, so I can replace both of those. I don't need to wait for parts, but it's something else that we need to do. I have to wait now for the power resistors. I can get them on Friday, so probably Monday I'll be back onto this. The trimmer pots, I can just change that now. I know what the problem is. I'll change them both and set them back to about the middle, and then hopefully find out how to balance this. I know somebody's going to tell me on here how to do it. And of course the other resistors as well, the open circuit base resistors. But I'm confident now that I can actually plug this in using the current limiting light bulb, of course. And it's not going to go bang, nothing drastic is going to happen. And I can probably then inject a signal into it. I think all the voltages will be balanced at least. And we can actually see if it's working properly. So there'll be a part 2. Okay, another video completed. It was a long one again, guys, but this work takes time. I'm hoping you appreciate that. I can't imagine any way to make this shorter and still teach you everything that I've taught in this video, to explain things, yeah. But hey, somebody go through one of my videos if you really want to waste some time. And not waste is the wrong term. If you want to spend some time, but it might be a waste of time, go through and you tell me all the bits that should be or could be edited out without removing any of the important content. Yeah. And then the reason it's a waste of time, because I might ignore that anyway. But there you go. Sorry about the loss of voice on this one. It's not getting a lot better, but I have to keep on working, and I guess I have to keep you guys entertained a little bit as well. Okay. Hope you learned quite a lot on that one. I learnt a few things again, or I came across a few things that my previous knowledge helped me with, like the floating voltage thing. Very strange as it looked, but now if you guys see such things, hopefully you will know how to determine what is really happening. Yeah, when it comes to transistor circuits, the voltage between the base and emitter is king. Yeah, that's the thing. That's the thing to measure if you're not sure. And measure it directly, not like comparing one voltage to the other and subtracting one from the other one, yeah, as you've just seen. I'll see you all soon, guys, on another Learning Electronics Repair video. Got quite a few things to do, things to look at, a couple of interesting things to review that I think you guys will be interested in as well. So I'll see you all very soon. Ciao for now.